Hello, I'm Takuma Kishimoto from Nagoya Institute of Technology of Japan. Thank you for inviting me to this conference as a speaker. Today I'll show you the experimental and crystal plasticity finite element analysis of surface roughening in hollow sinking. And this study focuses on the tube forming technology. Thin-walled fine tubes are used in many fields. Large diameter tubes are used for structural components and automobile parts, whereas small diameter tubes are used for medical devices. This study targets tube with diameter of 2 mm or less. To produce these tubes, the diameter of larger tubes must be reduced. Usually, fine tubes are manufactured by hollow sinking. Hollow sinking is a tube forming method that uses a tapered die. Drawing die is a tapered tool used to reduce the tube diameter. In this process, the outer diameter of tubes decreased as it passes through the die. Many tubes are mass produced at high speed using this method, like this movie. Thin-walled fine tubes produced by hollow sinking are widely used in medical devices such as stents that, that keep blood vessels open. In these applications, high surface roughness increases corrosion rate and can shorten the lifetime of the stent. So the inner surface roughness should be suppressed during hollow sinking, but the inner surface roughness often increases like this during drawing. This video shows surface roughening during uniaxial tension of a sheet. The roughening is caused by the grain deformation, individual grain deformation, because each grain deforms differently in both magnitude and direction. Local peaks and valleys are formed on the surface. So controlling grain deformation is essential for suppressing roughness on the free surface. In this study, I used crystal plasticity finite element method (CPFEM) to evaluate the grain deformation inside the die. This animation shows the free surface roughening of an aluminum sheet in uniaxial tension of the CPFEM. Grains deform by sliding along the specific atomic planes called slip planes. CPFM can reproduce this grain scale deformation by calculating the resolved shear stress, which drives slip in each grain. In hollow sinking, however, it is very difficult to experimentally observe the grain deformation inside the die during the process. As a result, the mechanism of roughening of the inner surface hasn't been clarified. The CPFM allows us to track how grains deform and how the surface roughness evolves step by step. Therefore, it can reveal how grain deformation inside the die leads to inner surface roughening in hollow sinking. In this study, I developed the first CPFM model to capture the time evolution of grain deformation inside the die. So the objective of this study was clarifying the time evolution of inner surface roughening and grain deformation of the tube inside the die during hollow sinking. Then we developed a CPFM model of hollow sinking and evaluated the evolution of surface roughening and the grain deformation on the inner surface. Next, I'll explain the FE model of the tube. I modeled 1/16 stainless steel tube with outer diameter of 2 mm, wall thickness of 0.1 mm using LS Dyna. In our previous experiment, tube had only 2 or 3 grains through the thickness, and the tube developed a strong 111 fiber texture along the drawing direction. To reproduce this, I built a Voronoi model with an average grain size of 17 micrometer and set orientations with 111 fiber texture. And we set the FCC slip systems to 111 slip plane and 110 slip direction. Using this workflow, finally I created a 3D structured tube like this. Next, CPFA model of hollow sinking. I built a 3-pass drawing model. The rigid die was fixed and the elastoplastic tube was drawn by prescribing displacement to this front end nodes in the drawing direction. The tube contacted the die here, and friction coefficient was set to 0.05. Our calculation followed Rosita's model. LS Dyna's main routine gives the current, deformation gradient, and stress to the user subroutine. For each slip system, I computed the resolved shear stress and slip rate with viscoplastic power law. I modeled the work hardening by as increase in CRSS. The increase in CRSS was modeled following the piece hardening law, and the hardening parameters were calibrated by fitting the CPFM stress-strain curve to the experimental curve. In the Pierce hardening model, each slip system starts with an initial CRSS G0. As shear accumulates on that system, its resistance increases and gradually approaches saturation values GS. So hardening becomes weaker and at large strain. Next, I'll present the simulation result. First, I checked whether this model can properly reproduce the inhomogeneous deformation of the grains. Here is accumulated shear strain obtained by summing the shear strain on all slip systems. This is a longitudinal cross section. Here is the tube. Here is the tube wall. Down here, you can see grain deformation on the inner surface. When the tube first contacted the die, the shear strain started to increase. As the tube passed through the die, the shear strain kept increasing, and it became different from grain to grain. So we confirmed this CPFA model could reproduce the inhomogeneous deformation in hollow sinking. Next, I evaluate whether this model reproduced surface roughening. This is grain arrangement on inner surface, and this is height map. The red regions are higher than surroundings, and the blue regions are lower. As the pass number increased, the red and blue areas expanded, so the inner surface roughness increased. This line surface roughness also increased by drawing. So we confirmed that the inner surface roughness developed by drawing in this model. Next, I evaluate the time evolution of inner surface roughening inside the die. This is the inner surface roughness after one pass. The position A became peak, and position B was valley. I plotted the time evolution of the ND displacement of the inner surface in each position. ND is the normal direction to the surface. Therefore, ND displacement directly represents the local upward or downward movement of the inner surface. By evaluating this, we can clarify how each grain contributes to inner surface roughening. This ND displacement doesn't include rigid body motion from sliding on the die. So this shows only the amount of grain deformation for ND. During the tube pass through the die, The energy displacement at the inner surface kept increasing in the positive energy direction. The energy displacement at position B also increased in the positive direction. However, its increase was smaller than that at A, which formed a peak. The difference between A and B was 5 micrometer, which agreed with the height difference 5 micrometer observed in the surface height map. This means that the inner surface roughness is formed differences in positive energy displacement from the outer surface toward the inner surface. What is important here is that the position B didn't show negative energy displacement. Position B became a valley not because it moved downward, but because it moves upward, less than the surroundings region. Next, I investigate the factors causing differences in energy displacement depending on the location on the inner surface. In this model, the wall thickness contains 2 or 3 grains. At position A, which became a peak in previous slide, I evaluate how much the grains on the inner and the outer surface side deformed in the surface normal direction, namely the energy direction. This figure shows the drawing time versus energy plastic strain rate in the energy direction. The energy plastic strain rate indicates how fast a grain plastically stretches or shrinks in the surface normal direction. A positive value means that the grain is plastically elongated in the energy direction, whereas a negative value means that is plastically compressed to the energy direction. First, focusing on before die taper region here. The energy plastic strain rate of inner grain increased in the positive direction, whereas that of the outer grain increased in the negative positive direction. This is because the tube changes its material flow direction along the die taper. As a result, the bending stress was generated here, so the outer grain was subjected to tension like this, and the inner side was subjected to compression like this in the drag direction. Because of this bending stress, the tensile side locally thinned in the energy direction, while the compressive side locally thickened. This led to the negative and positive energy plastic strain rate, respectively. Next, at the entrance of die taper here, the once bent tube is unbent and strained. This produced the deformation with the opposite sign to previous bending stage. Therefore, energy plastic strain became positive on the outer grain and negative on the inner grain. The key point here is that energy plastic strain rate reached maximum on the outer surface in approach region. Since outer surface is in contact with the die, like this, a large compressive bending stress acts here. This likely caused the outer grain to elongate strongly in the energy direction. After that, energy plastic strain rate repeatedly changed its sign because of similar bending deformation like this. All of these trends can be explained by bending deformation. Therefore, I found that the surface normal deformation behavior during the process is controlled by bending deformation. In previous slide, I focused on position A, which was a peak, but I also focused on position B, which was a valley. A qualitative trend of the energy plastic strain rate at position B was the same as at position A, but the energy plastic strain rate on the outer surface of B here, this value was lower than at A. This result indicates that the outer surface of B hardly pushed up the inner grain surface, so a lower position on the inner surface than at A. This trend can be schematically illustrated like this. A larger strain rate forms the larger strain rate of outer surface grain forms peaks by pushing up the inner surface, whereas smaller one result in valleys. So peak and valley formation is governed by the ND plastic strain rate of outer surface. This study provides a key new insight. The formation of peaks and valleys on the inner surface is governed by whether the outer surface grains can push up the inner surface. Finally, conclusions. In this study, the effect of the grain deformation in the die on the inner surface roughness in hollow thinking were clarified as follows. First, in the die taper region, the energy displacement from the outer surface toward the inner surface varies from grain to grain, and this variation appears as the surface roughness. Peaks and valleys formation is governed by any plastic strain rate of outer surface. A larger strain rate forms a peak by pushing up the inner surface, whereas a smaller one results in valleys. Thank you very much.